We're going to go ahead and take a look at universal gravitation. Now, I mentioned this briefly in Module 8.1, where we were talking about the forces that are responsible for holding the planets in motion around the sun. Okay? Universal gravitation explains the gravitational force that acts between two objects and how to calculate it. Now, a lot of people say Newton discovered gravity, which is just entirely wrong. Newton didn't discover gravity. Everybody has known about gravity since forever. When you jump, you fall back down to the ground. What Newton said was that gravity is universal. It's the same force that holds the sun in orbit, or the planet in orbit around the sun, as holds us to the surfaces of the earth, or makes apples fall out of trees. So Newton's big accomplishment was not to discover gravity, but rather to say that gravity is universal. It acts between all objects with mass. Okay? Gravity acts between all objects with mass. That's what it means when we say universal gravitation. And Newton actually figured out the equation that tells us how big the force is compared to the masses. F equals m1 times m2 times some constant g. This is a universal gravitational constant divided by the distance between those two masses squared. Newton never actually came up with a value for g, so he didn't actually have an equation, he had a proportion. He knew that the force was proportional to m1, m2 over r squared, where r is the distance between them. It wasn't until later that a man named Henry Cavendish actually figured out what the universal gravitational constant g was, and they say Cavendish found the mass of the earth, or weighed the earth with his experiment. Okay. So to set this up a little bit for you, what the Cavendish experiment was he had a torsional balance. And so he had two giant spheres of lead that were supported. And then on a beam that was free to rotate. So we're looking at a top-down view. So this was suspended on a little tiny cable that was free to rotate, and there was a mirror on this cable, so a laser could shine in on the mirror and shine back out, or a light beam anyways. He put two more masses, and then he measured this rotational angle. So what actually happened is, because of the gravitational attraction between these two masses, this thing actually rotated this way, and so of course that means his beam of light also rotated out this way, and he was able to calculate the tension in the cable, or the torsion in the cable, that was being caused by this gravitational pull between these two things, and he was able to work out a value for G. And the value that we use today, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, is the universal gravitational constant. It does not matter where you're at, what forces, what masses. When we're talking about gravity, the universal gravitational constant is 6.67 times 10 to the negative 11th newton meter squared per kilogram squared. You'll notice this is a very small number. The force due to gravity is weak. Okay, we're familiar with it because we're right on the surface of Earth, but it's not strong compared to the magnetic fields, right? Two little magnets have a huge magnetic force between them. Two little masses have almost no gravitational attraction between them. So it is worth noting that this is a small number. Now we can use Newton's second law to figure out the force of attraction between two masses. And I said that Cavendish experiment was said to have weighed the Earth. Well, if we look at why, let's say we've got the Earth down here. So this is the Earth, and it has some mass of the Earth. We don't know what it is, but we have something on the surface of the Earth, and we know its mass. Say its mass m equals 5 kilograms. We know from experimentation, if we drop this thing, it's going to accelerate because the force due to gravity acts on it, and that force is equal to mg. Well, this m is that m, right? It's the mass of the object. So if we look at Newton's second law, net force acting on this object is Fg, and that is equal to m, and I'm going to call this m, just m, g. Okay? But according to Newton's law of universal gravitation, the force acting on that, the force due to gravity, is a result of the two masses acting together. So Fg is equal to m1 times me, where me is the mass of the Earth, divided by r squared times this universal gravitational constant g. Capital G is not the same thing as lowercase g. Lowercase g is the acceleration due to gravity on Earth. Uppercase g is the universal gravitational constant. Doesn't matter where you are, they don't measure the same thing. But you'll notice this Fg can be substituted here. Okay? Or this m1 is the mass of our object. So I have mg equals me times m times g, universal gravitational constant, divided by r squared. Well, the mass of the object drops out, and we have g equals the mass of the Earth times the universal gravitational constant g divided by r squared. And you're thinking, well, if this object is essentially on the surface of Earth, what is r? How can we know that? Well, it turns out we measure the the distance between things from their centers. So this is just the radius of the Earth. And the radius of the Earth had been known for a while because actually it was geometry and some stories about shadows on the bottom of a well that lets you calculate the radius of the Earth. But once you know the radius of the Earth, we know the acceleration due to gravity. What we can say is the acceleration due to gravity times the radius of the Earth squared divided by the universal gravitational constant g gives us the mass of the Earth. So once we knew this value, and we already knew those two, so calculating the mass of the Earth was not a super tricky thing to do. So when Cavendish actually found that value for the universal gravitational constant, we were able to see how much mass the Earth had. And then, once we knew that, it was just a matter of using that to figure out the mass of the Sun. Because if the Sun's here, Sun, it has some mass, and the Earth is here, mass of the Earth, we know the separation between them from here to here, where that has some distance r. We just found the mass of the Earth, and we also know the period of the rotation. We know t equals 365 days. And remember, there's multiple formulas for centripetal acceleration, but one of them, mass times centripetal acceleration, is m times 4 pi squared r over t squared. Okay? So this r is the distance between the Sun and the Earth, and t is the period in days or hours or seconds, however you want to do it. Probably we'd use seconds, so we would be in base units. But then we can say F, the force of gravity between these two things, is equal to the centripetal acceleration of the Earth, so mass of the Earth times 4 pi squared r over t squared, but that's also equal to the mass of the Earth times the mass of the Sun divided by the distance between them squared times the universal gravitational constant g. And we now know the mass of the Earth, we know the distance between the Earth and the Sun, we know g, we can figure out the mass of the Sun. Okay, so when we knew the universal gravitational constant, it allowed us to calculate the mass of our planet, and once we knew the mass of our planet, we could calculate the mass of the Sun. And once we knew the mass of the Sun, we could calculate the mass of all the other planets because we can measure their orbital periods and we can measure their distance from the Sun to them. So it is an incredibly powerful thing that Newton and Cavendish collectively did to find the universal gravitational constant and come up with the law of universal gravitation.